Hi there, my name is Thomas Cauchy, and I am a researcher in chemistry, in computational chemistry. And I would like to present you today our research team, Quchempedia. Some of you may even participate, since our project has a collaborative approach through Boeing calculations. And I will present this in a later episode. Today I would like to present the origin of our project, so you can understand why if you want to participate, how to, and what is research. The goal of this playlist is to explain to the public what is research in chemistry, in computational science, and I hope it will be interesting for a large audience. Let's start to present myself and my background. So my name is Thomas Cauchy, and I made my master, my fifth year of study in informatics and in computational chemistry and theoretical chemistry. So I'm French, and I made my studies in France in different cities, Nancy and Rennes in Brittany. Then I had the opportunity to go to Barcelona to do my PhD and to finish my studies there. So it was concerning my theme there was molecular magnetism. So we study the magnetic property of one molecules, big ones. Then when you get your diploma, few obtain directly a permanent position. Usually you start short terms, 1 year, 2 years positions, where you can get new competencies, you develop new techniques. And I went to Rennes, where I made my master, to understand the excited state calculation, for example. So I will come back to that later. Then I followed it by 1 year in Angers, where I am now, to do a short 1 year position of both teaching and researching. And I obtained a permanent position in 2010 in Angers as a maître de conférence. In American equivalence, it's an assistant professor or lecturer in English, where you have both teaching and research. But also in France you have some work in academic administration and bureaucracy. And one of my missions in France is to do some scientific popularizations, to present what is science to the public. And clearly this is one of the goals of this playlist. So you see, I've made a full circle. I start in Rennes, then Barcelona and Angers, then Rennes, then Angers. And now I work in a laboratory that is called Moltec Anjou. It is a medium-sized laboratory with 50 permanent positions. So in French, you have more permanent positions than usually in the Anglo-Saxons. In the Anglo-Saxon, you have few permanent and more short-term positions, and in France you have more permanent but less money for each one. So maybe we will talk about it in future episodes. So in France you have fully researchers, enseignants-chercheurs that are teachers and researchers like myself, engineers and technicians. And our lab has two heads, like more or less, that is the CNRS, that full research, and the university. And we have like around 30 people in short-term positions, that is PhD, that are studying to finish their thesis, and postdocs, post-doctoral positions. A little bit of geography. Angers is a city in the Loire Valley, Here we have Brittany, and here we have the Pays de la Loire. The big city in this region is Nantes, here in the end of the Loire, near the ocean. It's a medium-sized city, 200,000 inhabitants, and a large student population, and with a rich history. We have in the middle of the city a castle that was made to stand on a military. It's not a Loire castle for just leisure, okay? And it's quite imposing, but because they cut the head of the towers to prevent it to be totally razed. So back to the lab. The goal of our lab is to produce and understand materials that are based off organic molecules or hybrid organic-inorganic. Organic, that means that you have only carbon, oxygen, sulfur, nitrogen, for example, where inorganic you have metals like iron, manganese. And our materials are designed to store energy, for example, to produce current like photovoltaics. And photonics is the properties that depends on the interaction with the photon. And we also produce stimulable materials and nanostructuring materials. One of our key goal is to understand with small molecules how we can do and establish relationships between the structure of the molecule and the property. We are not going to very complex system where you have you don't fully understand why you have, for example, a huge yield, and we prefer to produce small compounds and to understand how we can modify, intensify around this compound to understand how we have a better yield or a lower yield of the property. And we have a multidisciplinary approach. We have physicians, we have chemical synthesis experts, we have coordination compounds experts, we have physical chemistry, theoretical chemistry like myself, and analytical chemistry. And it's a great place to do a PhD because our students, doctoral students, can learn from a little bit of everything. If you want to know more about this lab, you can follow the links here to see what kind of research we're doing. And this is one of our master studies that is concerning the materials around light and matter. Let's take one example of an article of a science where I participated. It's a recent one. It's not it's not part of the Quchempedia. I will do episodes where I explain to you what, for example, what is your contribution to the Quchempedia research. But for now, just what is an example of research of Moltec-Anjou? And research is a collaborative approach, okay, like you see. For example, so we have here a journal, Chemistry European Journal. It's a multidisciplinary generalist journal concerning chemistry. Some are dedicated to physical chemistry, theoretical chemistry, or organic synthesis. And in Chemistry European Journal, you have a little bit of everything, and it's for generalist research. You can find the journal here, but it's not in open access. So for those of you who are studying in universities, you may have access of this full article. Articles are quite specific. You see that the title is really specific. It's concerned perilene diimide, so a kind of compounds where we want to do a nitro substitution. And the goal here is that for people that are working on perilene diimide to understand rapidly if they are interested in this kind of article, in these results. So if you do perolendiamide and you use this Suzuki-Miura reaction, maybe you will be interested in reading this article. There is several authors. Usually the first names are those that contributed the most in time and effort. And the last name are the veteran or experts that lead the research. You will find here two groups. We have 4 people that contributed to the organic chemistry, synthesis, and physical characterization, like UV visible properties, and Magali Alain, a colleague that is specialist in the X-ray diffraction. So it's an analytical chemistry experiment that allow us to understand what are the atoms in the space. And myself, that is responsible here for the computational chemistry results. Let me present you what is my contribution in this article to understand and to explain to you, illustrate what is computational chemistry and how is it useful. We have here some perilene diimide compounds. So perilene is the core here, diimide is this part, and usually we do some substitution with bromine to form more complex compounds, and we can add a new substitution with interesting electronic properties. However, even if we have 2 bromine, usually we don't manage to do a D-substitution, a second substitution. And here we show that using a nitro substitutions, we have 2 nitro substitution, and we can get and manage to a D-substituted compound. To understand why it is interesting to have and how the reaction works, we had to do some calculations. So to understand those kind of properties, we need quantum chemistry. Quantum chemistry is quantum mechanics, Schrödinger equation, resolved, and it's quite a costly process in terms of computations. It depends on the number of electrons, and here you have molecules that are medium-sized. So if you want precise results, it will take days. In the end, between the different results, we can extract here, for example, we have the LUMO energy. That means that it's a level of energy where there is no electrons, but if you add an electron in this compound, it will go to this level at around this energy. If the energy is quite low, that means that this compound favor or attract more the electrons than the others. So this is the most accepting compound, okay, and this one is the less accepting. So you can then understand the relation between accepting power and structure. And those pictures here depend on the charge of the compound. So red parts means that there is a negative charge, and blue part is positive charge, where there is a need or where you can accommodate new electrons. So here you can understand that there is more blue parts, and it's responsible of the more accepting powers. So this is not revolutionary, but to understand the electronic properties, you need quantum chemistry, and you need molecular computational chemistry. And now you have computers atoms that can do easily those kind of calculations. Yes, you will not focus 2 days of your computer for this kind of calculations, but the price of a computer now, your computers are more potent than the Manhattan Project computers, calculators that allow for the making of the atomic bomb in the Second World War. So computational power is easily is quite cheap now, and we produce a lot of different compounds, and you can do the calculations before doing the organic synthesis. So sometimes it's quite interesting to do the computational study beforehand, before the organic synthesis, and maybe to discriminate what are the most interesting goals. And you can do it for photovoltaics, OLED, or many other properties. And sometimes you also want to do the most simple compounds, or maybe the most feasible compounds, more easy to synthesis. And then when you do the synthesis, you can discuss, was it easy? Is it can you manipulate and process the compound to do a material? So quantum chemistry is now almost a mandatory tool. If you do a large scale research, you need calculations beforehand and after in terms of rationale, and you can do such accurate model and predictions. However, how does it work? So you take a molecule, for example, and you do some quantum chemistry and you obtain some properties. For that, you need some inputs. That means that you prepare a document with the commands, the data. So quantum chemistry and Schrödinger equations cannot be done when you have more, or cannot be done exactly when you have more than one electron. You need approximations. So you need to choose a correct method. There is high-level approximations that will cost more in terms of computational power, or lower approximations, depending on how much time you have, how much memory do you have, and how much precise you need the calculations. Okay, so this is clearly one of my key competencies, to understand what is the best approach. And then you need to ask him what kind of properties you want, and you need to give him the information of what are the atoms, where are they in the space, and what is the total charge and multiplicity, for example. Then you give this input to quantum chemistry programs. Some are quite efficient and they are not cheap, for example, but they are not free, open source. There is some solutions that are open source that are less optimized, but at least the code is open. Okay, and our calculation process is an iterative one. That means that it will change some parameters until he finds the best energies. So it's based on a minimization process. Those of you that can understand French, you can see in my page that I do some introductions to quantum chemistry, and I explain in details how do we do the resolution of the equation Schrödinger, but it's in French for my students. This calculation cost scales with the number of electrons, not linearly, but quadratically. That means that if you double in size, your computational time will more than double in size. In the end, you obtain an output file or several output files where you will find all the process and the results that you ask for normally, if everything converges to the right result. Now, the problem. I am the only computational chemist specialist for all the lab. And the demand is much higher and I cannot process everything. So usually I form the students, the PhD students that want and needs calculations, and some of my experimental colleagues are also trained to be able to launch the calculation. If you know a little bit about computers, in 2 days I can explain to you how to prepare your inputs and launch your calculations. And if everything goes right, it's easy to extract the results that you want. It's quite harder to assess if really the compounds or the calculations converge to the right result, and if everything went smoothly. And usually this quality control is quite lacking, and we don't have programs that usually are robust enough. And I will comment on this in future episodes. And then, what happened to the results? Usually they are destroyed. So everywhere on Earth, there is many molecular calculations, and we don't have an encyclopedia where you can easily find them. And this is a problem. I think it's a huge waste of computational power. Most cases of when you have a problem can be handled by the same procedure, in Moltec-Anjou at least. So I thought about automation, how to do an automatic program that will scan the results and make a form that presents the result, but maybe also future properties that could be interesting, and to assess the quality control. Such program needs to be efficient and robust, and so since I am a computational chemist, I know a little bit of Python, I know a little bit of C, but I don't know how to do such program. And usually when chemists do their program, they are not, I don't want to do a generalization, but there can be flaws. They are far from perfect. If you have some computational computer science specialists or programmers, you can have a better solution. And we had a serendipity moment here when I thought about this in an out of context moment. I met Benoit, who is a researcher, teacher in informatique. In French, we have the term informatique that envelope or that had computer science and data science, and he has both competencies, and he is interested in biology and chemistry. So we had a serendipity, a fortunate moment where an unexpected encounter will change our program. And for the next week, next episode, I will tell you how Benoit changed all this program, and this is the Quchempedia project. So the context is there, and next time I will tell you what is now the Quchempedia and what are the objectives. I hope that you can find this video interesting and you will want to see the rest of this. You can comment and like the video if you want, and I will see you next time. Bye.